Okay, so let's talk about adding and subtracting fractions, or rational expressions as they're known as. Remember, rational is a fancy name for what? Hopefully you said fraction, and that's what we're going to be dealing with. And you know as well as I do that in order to add and subtract fractions, you need to have a what? That's right, hopefully you said common denominator, because if you don't have a common denominator, you're not able to add those fractions together. Got it? Cool. Okay, here we go. So these are our objectives for this particular section. Adding and subtracting fractions that have the same denominator, which makes things easy. Finding a common denominator just in case the fractions don't have the same denominators. And then finally adding fractions without a common denominator. So if they already have the same denominator, that's easy enough. We notice that these denominators are the same, which means we can just add p plus r together. Remember, the denominator never changes because the denominator tells me the total number of pieces that are in that object. For instance, if there's an object cut into 4 pieces, then your denominator would be equal to 4. So that never changes. It's the total number of pieces in this object. Again, I need the denominators the same when I'm subtracting, and when they are, I can just subtract the numerators straight across. And again, the denominator does not change. So, notice what it says. To add and subtract rational expressions with common denominators, simply add or subtract over. By the way, the very last step of adding and subtracting fractions that they didn't say, the very last step is to always see if you can reduce that fraction. And just like we discussed in multiplying and dividing these rational expressions, you need to make sure that there is multiplication in between those items that you're trying to cancel out. Multiplication is a must if you are going to do any kind of reducing whatsoever. So let's take a look at our first example. They ask us to add. We know how to add. We have to make certain the denominators are the same. Gratefully, they are. And that means we can add these numerators across. Now, for us visual people, we may want to put a 1 in front of this x. So we remember that we're literally supposed to be adding an 8x and a 1x together, since the denominators are the same. Okay? And you know as well as I do what 8 plus 1 is. Cool. Now, question. We've added, yes? What's the very last step we're supposed to be doing? That's right, we're supposed to see if we can reduce, but before we see if we can reduce, we need to make sure there is multiplication in between this 3 and y, and in between this 9 and x. And gratefully, there's multiplication in between them, which means we can look at them separately. We can almost look at it as 9 over 3 multiplied by x over y. Gratefully, we can cancel out the 3 and the 9. We can't do anything with the x and the y, which means we are literally multiplying these two fractions together, if you want to think of it like that, which means you would have an answer of 3x over y, which is exactly what they have. Good? Cool. Let's try another example. Gratefully, these denominators once again are the same, and since they are the same, we can do the addition problem that they have given us. And again, for us visual people, we may want to put a 1 in front of that x. So we remember that it is literally a 1x plus the 7x we're adding, which gives us 8x. And again, the very last step that we're supposed to see if we can do is to reduce. But to reduce, you need to make sure that this is multiplication, which gratefully it is multiplication. Let me try writing that word just a little bit better. Okay, since it is multiplication, I can basically look at it as 8 over 6 times x over 1. And you know as well as I do that we can reduce both the 8 and the 6 by 2. which means I basically have 4 over 3 times x over 1, which would give us 4x over 3, and the book agrees with us. Yay! Okay, let's get another example here. Now they're asking us to subtract. And when we subtract, still have to make sure the denominators are the same. Gratefully they are, which means we're going to do 8y minus 16. Now, question. Does the 8y, or pardon me, the 8 is multiplied to a y, right? But does the 16 have a y? No y, which means you literally cannot do 8 minus 16, which is why it is written as 8y minus 16. I cannot subtract those, so technically I would be done with subtraction. But the last step is to see if we can reduce. And in order to reduce, you need to make sure that this 8y minus 16 is a multiplication problem. Is it a multiplication problem? Yeah, no, it's not. This 8 times y, that might be multiplication, but there's a minus sign keeping that 8y with the 16, which means in order to turn it to multiplication, yeah, you're going to have to factor. And the first step of factoring is to factor out what's in common, what's the greatest common factor, which is why you see them write the next step. Notice now I do have multiplication in between the 8 and the parentheses. This is multiplication. Since it is multiplication, I can go ahead and cancel. And when I cancel, all I'm left with is 8. Does that make sense? Cool. Okay, let's talk about finding a common denominator when they don't give us the same denominators. You are going to have to find it. Okay, that's basically what this slide is telling you. First step, extremely important, you're going to have to factor. Regardless of what they give you, the first step is always to factor. And then the second step, I phrase the second step just a little bit differently than they do. Okay, the authors of the book have their way of saying things. I have my way of saying things. My second step is to make the denominators look the same. And we do this we accomplish this by multiplying each denominator by what it is missing. So I just have a little bit of a different way of phrasing this step. So let's take a look at an example. There's a comma between here. They're not asking me to add or subtract. They're asking me to find the lowest common denominator, which means I am dealing with a 6y and I am dealing with a 4y plus 12. So here's the deal. We're going to look at the 6y, and we are going to notice that we can rewrite it as 2 times 3 times y. Great. We're going to look at the 4y plus 12, and we're going to notice that there's something in common. We can take out that 4, which leaves us this parenthesis of y plus 3. And the 4 can even be factored to 2 squared. Now, I'm going to be honest with you. I think the better way to write this is 2 times 2 times the parenthesis of y plus 3. That is my suggestion. Now, remember my second step, the way I phrased it? It's a little bit different than how the authors phrase it. I need to make sure that this denominator of 2 times 3 times y looks exactly the same as this denominator of 2 times the parenthesis. Well, the one thing that I'm noticing is this first denominator to look like this second denominator is missing another 2. So I'm going to multiply by 2. Something else I'm noticing it's missing is this y plus 3. So I am going to take the first denominator and I'm also going to multiply it by y plus 3. Does that make sense? Okay, so now the first denominator has 2 2's and so does the second denominator. The first denominator also has a y plus 3 and so does the second denominator. And now I'm noticing that the second denominator is missing this 3 times y, which means I'm going to have to multiply it by 3 times y. And now they look exactly the same, which means your common denominator, your LCD, is going to be made up of 2 2's, a 3, a y, and a parenthesis of y plus 3. Which means you've got 4 times 3y times the parenthesis of y plus 3, and then you end up with 12y times the parenthesis of y plus 3. Don't distribute any further. I never multiply the parentheses together, ever. You'll see why as we go through some examples. So noticing, then 3y is what they need. The 2 2's, the y plus 3, which is exactly what we have. We have the 3y, we have the 2 2's, and we have the y plus 3. So their common denominator is exactly like our common denominator. Good? Okay, let's try another example. Again, the directions say find the LCD, which means I am going to look at just these two denominators. And the first step of finding the LCD is to do what? Hopefully you said it. First, you're going to have to factor, just like we said in the previous slide. So, you guys factor, and hopefully you agree with both of these denominators being factored form. Now, remember what I mentioned. I look at it a little bit differently. I need this first denominator to look like this second denominator. So the question I ask myself is this. What's missing? I'm noticing the first denominator has an x plus 3, just like the second denominator. But I'm noticing the first denominator is missing this parenthesis of x plus 7. So I'm going to multiply it there. And now they both have an x plus 7. And now I'm noticing the second denominator is missing the x plus 1. And now it has an x plus 1 just like the first denominator. Which means, since they both look the same now, our common denominator is going to be made up of these three parentheses multiplied together. X plus 3, x plus 1, and x plus 7. Definitely do not multiply these parentheses together, okay? You will see why when we start adding and subtracting them. Okay, one more example. Again, we're finding the lowest common denominator. Here's my first denominator, here's my second denominator. What's my first step? That's right, first thing you're going to need to do is factor. By the way, that's always an if possible, because sometimes it's not possible to factor these denominators. Okay, now, hopefully you can factor them. You agree with their factoring, all right? Notice in this first factoring, they had a 5 in common. So they took out the 5 first, and then they kept factoring this parenthesis because they noticed the x squared and the 1 are both perfect squares. So they were able to continue factoring. And here's denominator number 2 in factored form. Again, my recommendation is this, to write this denominator out twice. Do not leave it with the square. Why? Because most of us are visual people, and we need to literally see the two x minus 1's written out. All right, here we go. Remember, we need to make these guys look the same. I'm noticing the first denominator has an x plus 1, but the second denominator does not, so it needs an x plus 1. Check. I'm noticing the first denominator has a 5, but the second one does not, so it needs a 5. Check. I'm noticing the first denominator has an x minus 1, and so does the second denominator. But I'm noticing this first denominator is missing the other x minus 1. Now it has them both. So, in our case, what we are telling ourselves is this. We are telling ourselves that the common denominator, the LCD in this case, is going to be made up of a 5 and x plus 1 and 2x minus 1s. I would leave it written out this way. I wouldn't put the x minus 1 squared. I will literally leave it that way. And they agree with us. Again, they wrote it with the square. I don't recommend it. All right? Okay. Oh, I lied. One more example. Now, here's where the authors of the book and I differ a little bit. Because they will tell you that since these two denominators are basically the same but in reverse order, choose either one. I don't really agree with that. Remember the first step of factoring. The first step of factoring is, if possible, reduce, right? So first, or pardon me, to factor. So, I am going to look at each denominator and I'm going to see what we can do. The first denominator is x minus 3. Can this be factored? No. So it's just going to remain x minus 3. The second denominator is 3 minus x. I'm noticing this is not in descending order, which means when I put it in descending order, the negative x comes first, the positive 3 comes second. Since the first term is negative, I know I'm going to factor out a negative something, and in this case it's just a 1 they have in common. And when I factor it out, I'm left with x minus 3, aren't I? So, I have an x minus 3, and I have a negative 1 times x minus 3. Good? Okay, so I could multiply this first denominator by a negative 1. Hang in there a second. You'll see how we actually handle these. That'll make our lives just a little bit simpler. Okay, so let's go on to adding and subtracting fractions that don't have the same denominator. First, you need to find a common denominator. Second, you need to multiply by what's missing. This is what this is saying. Equivalent rational expression. Denominator is found in step 1. You need to multiply what's missing. And then you can add or subtract the numerators as you need to. And this step is the last step, which is to reduce. That's what simplify means, reduce. Okay, so workspace for number 6. So let's look at example 6. Okay, so we're adding these two fractions. 7 over a to the third plus 9 over 2a to the fourth. What's our first thing we need to do? All right, first things first, we need to find a common denominator. So, that's what we need to find. So let's go back to our workspace. We need to find a common denominator. We need to find the lowest common denominator. That's our goal. So I have two denominators. I have an a to the third, and I have a 2a to the fourth. Our first step is to factor if possible, right? Okay, so, these don't look like they could factor because they're not polynomials in terms of there's no adding and subtracting to them. But I beg to differ. I know a to the third means a times a times a. I know 2a to the fourth means 2 times a times a times a times a. So for us visual people, this isn't a bad step to do. Now again, I need to make them look the same. So I notice both of them have the 3 a's. That's wonderful. But what I'm noticing is second denominator has a 2 and an a, but the first one does not, which means I need to multiply this first denominator by a 2 and an a, which tells me that my common denominator is going to be made up of a 2 and 4 a's, or better written as 2a to the power of 4. So there's our problem that we're working on to add. There's our common denominator, which is what we said. Now remember what we had done. We said that the first denominator needed to get multiplied by a 2a, didn't it? So notice what happens as we start adding these. First denominator needed to get multiplied by 2a. So we multiply the bottom and the top by 2a, which means that numerator now becomes 14a over 2a to the fourth. The second denominator stayed the same. We had nothing to do. Now let me ask you something. Since the denominators are the same, are we able to add? Yes. But does this 9 have an a? No. Which means you are simply going to have 14a plus 9. Last step is to reduce, remember, and that's my question. Can I reduce? And in order to reduce, you have to see if you can factor. Can I factor? Nope. So since I cannot factor here, I cannot cancel anything out. Remember, we talked about this before. Remember, addition and subtraction act like super glue. This is super glued together. So you cancel the 2 with the 14? Good job. You cannot, which means your final answer will be 14a plus 9 all over 2a to the power of 4. That's all you can do. Cool? All right. Let's look at the next example. And here's our workspace for it. Our next example is a subtraction problem. And these denominators are not exactly the same, are they? Okay, let's go back to the drawing board over here. So, first things first, LCD is needed. I have a 2x minus 6, and I have a 6 minus 2x, don't I? All right, so remember, first steps first. See if you can factor. I'm noticing on this first one I can take out a 2, and I'm left with the parenthesis of x minus 3. On the second one, not descending order, is it? Guess I should put it in descending order first. And then I'm noticing I can take out that negative 2, and I'll be left with x minus 3. So, what do you think? So far, so good? Okay, now, let me show you the next step on our workspace. All right? I have got the two fractions now. The first fraction is 5 over the 2 parentheses x minus 3, right? And I am subtracting fraction number 2, which had a 3 on the top. And now its denominator is negative 2 times this x minus 3. Agreed? Now, we've spoken about this before, but let's make sure we're on the same page. Do we ever like to have a negative left in the denominator? No. So what we can do is we can either move it to the front of the whole fraction, or we can move it with the 3. Either way, it still makes the fraction negative. So, regardless of which position we move it into, our next line is going to look like, first fraction stays the same. I am subtracting, and here is the 3 over the 2x minus 3, and I am going to take that negative and I am going to put it out front of the fraction, which makes the whole fraction negative. Remember what happens with a double negative? It turns out to be what? Yeah, that's right. That turns out to be positive, which actually means this addition or subtraction problem wasn't really a subtraction problem. The subtraction problem is really an addition problem, and these were the two fractions I was supposed to be adding. Now, let's take a look at the work that the book is doing. The one step they didn't show you is how it changed to addition, which is why in our workspace, you can see why it is an addition problem because of that double negative that happened. That's how they ended up with this addition sign. So we have 8 over 2x minus 6. Agreed? Okay. Remember what our last step of factoring is? Or pardon me, remember what our last step of adding and subtracting fractions are? Yeah, we have to see if we can reduce. And we reduce by doing what? That's right. See if we can factor. Clearly we can't do anything with the 8. Now remember what I said. This is why I leave the denominator in factored form. This is why I never multiply it together. Because I can see right away that the 2 and the 8 are going to cancel. I can see right away that they're going to cancel. Whereas the book, leaving them in multiplied form, creates an extra step of work for them to do that we don't have to do. But gratefully they agree with us. Good? Okay. So, let's take a look at another example. First things first, we're going to have to find the what? Yeah, common denominator. So, I'm hoping you remember how to factor those two denominators. There they are. And, do they look exactly the same? Yeah, no. So we need to make them look the same. I notice they both have an x plus 2, so we're good with that. But I'm noticing that this second denominator has an x plus 3, which this first one's missing. So I know I'm going to have to multiply it by x plus, let's find a better spot to put that. So I know I'm going to have to multiply this first fraction by an x plus 3. But just not the denominator, also the numerator, right? And then now they both have x plus 3's. Check. But I'm noticing the first denominator has this x minus 3 that the second one doesn't. So we need to give it the x minus 3 also, but if you do it to the denominator, you got to do it to the... Good. Now they both have the same denominators. Okay, so answer me a question. I'm supposed to add these two fractions, right? And since I'm supposed to add these two fractions together, and I'm noticing my numerators are multiplication problems, what do we do first? Do we add first or do we multiply first? What do the order of operations tell us? Good, you multiply first, which is why this 4 times the parenthesis of x plus 3, this is how we got the 4x plus 12. And the second numerator of x times the parenthesis x minus 3, this is how we get the x squared minus 3x. Okay, combine like terms now, and this is what we have. Okay, so what's the last step? That's right, the last step is to see if we can reduce, correct? Which means in order to reduce, you're going to have to see if you can what? Yep, there's that word again, factor. Boy, factoring plays a huge role in finding not only the common denominator, but also in reducing, doesn't it? Okay, so check it out. If I want to try to factor this x squared plus 1x, because there's a 1 there, plus 12, I take the first number, which is 1, and I times it by the last, which is 12, which gives me 12, doesn't it? Okay, let's look at our combinations. Positive 1, positive 12, or negative 1 and negative 12, right? Positive 2, positive 6, or negative 2 and negative 6, right? Positive 3 and positive 4, or negative 3 and negative 4, right? Do any of those add to a positive 1 in the middle? No. So can we factor this polynomial? No. Can't factor it. So can we reduce this fraction? Nope. So you couldn't factor the numerator. How am I going to cancel it with anything? So that wonderful looking fraction is your final answer. Cool? All right. One more example. They have given us 3 fractions to add together. And we need to make certain we have a common denominator to add them together. Remember, first steps first, factor. First denominator isn't factoring. Second denominator is factoring, which is why they pulled out this x. Third denominator, not factoring. Right? Okay. Which explains why our common denominator is simply an x and the parenthesis of x minus 5. Now remember, we have to make all these denominators look the same. So this first denominator has the x minus 5, and so does the second denominator. Does the third denominator? Nope, so we need to multiply by x minus 5. Just on the bottom? That's right. Top also. Second denominator has an x. Does the first one have an x? No, so I got to multiply it by x, bottom and top. And the third one has an x also, so we're good. All 3 of them have an x. All 3 of them have the x minus 5. We're good. Which explains why their next step looks exactly like ours. They multiplied the first fraction, top and bottom, by x, just like we did. They multiplied their third fraction by x minus 5, just like we did. And they didn't multiply fraction 2 by anything. We didn't multiply fraction 2 by anything either. Okay, so we have addition and subtraction now, don't we? But we also have multiplication. Which comes first? That's right, multiplication. Which is why the first numerator is 6x. Second one stayed the same, and the last one is now 2x minus 10. So far, so good? Okay, so now we get to add and subtract, don't we? Now, here's a little side note for you before I move it on to the next part. Do you notice this 2x minus 10 has a negative in front of the whole fraction? Question, does this negative only apply to the 2x, or does it apply to both of them? Yes, it applies to both of them because it's in front of an entire fraction, which means that 2x is definitely negative, like we knew it would be. But that negative 10 isn't a negative 10, it is positive because you had to distribute, which is why the next line looks like this. Does this make sense? Good. Now we can add things together, can't we? And boy, that simplified to something very nice, didn't it? Okay, so we were able to add and subtract because they actually gave us both to do here. And the last thing is to see if we can reduce. And in order to reduce, we have to see if we can do what? Yep, I know you're getting tired of hearing me say the word factor, but we're going to have to factor. Now, can we factor that numerator? Because the denominator is already factored. Sorry about that. Hang in there. I'm hoping you said yes. I'm hoping you said that the denominator of 5x minus 25 can be factored. I'm hoping you're noticing you can take a 5 out of both of them. And when you take a 5 out of both of them, you're left with this wonderful looking problem, which means the x minus 5's cancel, and you're simply left with, that's right, 5 over x. Okay, so hopefully this made sense to you. You have fun with homework, and I'll catch you on the flip side.